So this is chapter 10, section 2, number 41. They want you to find the power series for this. And once again, we could create that using the Taylor polynomial formula that we had in 10.1. But that's a lot of work. Instead, they ask us to use a known power series for 1 over 1 minus x. This is it here. And we know the absolute value of x must be less than 1 for this to converge. So how do I go from here to here? And there's a hint. In the title, it says use differentiating and integrating. So let's rewrite this and see which one we're going to use. So this is 1 minus x to the negative 1 power. This is the equivalent, okay? Now, if I take the derivative of this, the negative 1 comes in front, and this decreases by 1, becomes a minus 1, which is negative 2. But a negative 2 power is that. So clearly, I want to take the derivative of both sides in order to end up with that. So you have to just see what is going to get you what you want, because if I integrated this, I'm going to get the ln of that. I don't want the ln of that. I want that. So you just have to be creative and realize what's going to happen. So I'm going to take the derivative of both sides. That's kind of ugly. ddx of the whole thing, ddx of the whole thing. So this will be negative 1 minus x to the negative 2 power equals, and the derivative of 1 is 0. The derivative of that is 1, and then you get 2x, 3x squared, plus dot, 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 plus nx to the n minus 1, plus dot, 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 which is, and then on this one, the k is going to come in front, and this becomes k minus 1. So let's rewrite this. I'm just going to copy and paste this because I have the power. Bammo! Look at that. So when we take the derivative of that, it's really that. And since it's not x to the negative 1, it's box. So the negative 1 comes in front, which is here. Subtract 1 from the exponent, which is that. But then I have to multiply by the derivative of box, which is negative 1. So I need a negative 1 here, which makes that positive. And that makes this the answer we're looking for, which is wonderful. But let's double check something here. Our indexing to make sure it's pretty. If I plug in 0 here and here, do I get the first term? I don't, right? Now it kind of messes things up. Technically it's not wrong, because if I put a 0 here, your first term is 0. Then if I plug in a 1, I get 1 times x to the 0, which is 1. I get that. So it does get it eventually, but it's just not pretty. So we want to re-index this. And don't let this freak you out. It seems very strange, but it's just bookkeeping to make things pretty and nice. So we're going to change the starting number here. Instead of 0, we're going to start at 1. Oh, why is that 1? That should be infinity. Okay, but let's make sure it works out. I replaced that with 1. Oh, there's 2 ways I could do this. I'll replace it with 1. Therefore, if you put a 1 there and a 1 there, you get the first term, and we are bueno. So that works just fine. But I'm going to show you something else here. Someone might say, but I don't want to start at 1. I want to start at 0, because the original started at 0. I don't want to change it. So you could start at 0 instead. But if I start at 0, I am starting at 1 less than what I'm supposed to start at. So if I'm starting at 1 less, I need to replace these with 1 bigger to make it balance. So that would become k plus 1 x to the k plus 1 minus 1, which becomes this, k plus 1 x to the k. So there's a couple different ways you can write it, but I just want to show you, and it's not just that you're comfortable with that. It's not anything magical or strange.